This title is a little bit of a misnomer. I'm going to be talking about dynamic embeddings and how we use them to analyze text. They're actually a special case of an exponential family embedding. And the research question that we use for this story is sort of to understand how data science skill sets have evolved over time. So we've heard a lot at this conference about how it's a really new and exciting industry and it's seeing a lot of growth. And the question that we had and the data sets that we've been using are using job descriptions to understand how those have changed to this point right now. And so this is sort of a hybrid talk in some senses. On the one hand, I'm mostly going to be talking about the natural language processing tools that we use and different approaches you could use to address this question and what we found works. And specifically what I'm going to talk a little bit about is the constraints of having not a ton of natural language data and how this is a really robust method to deal with that sort of side of things. But then on the other hand, it is a little bit about data science skill sets and text skill sets and how actually they're cross-pollinating over time and changing. So you'll get a bit of both, especially towards the end about that sort of topic. So my company that I work for is a company called TapRecruit. We help companies write better job descriptions. And so our goal is to make the recruiting process more fair and more efficient. And one of the key issues that we deal with is when you're dealing with job descriptions, it's a lot of unstructured text. You can extract some structure from some of it, but mostly, largely, our problem is sort of machine comprehension of text and trying to extract skills and qualifications from this. And you can see how this functions as a job seeker. I'm sure you've all experienced this to various degrees, where the title of a job, which is what a lot of search engines are optimized for, doesn't get you the same type of results when you look at it. So, in this case, it's an example of a finance manager role. It can be either a very senior role or a very junior role. We have these issues also with roles like analysts. Data analysts versus an equity analyst are quite different roles with different requirements. And even if you narrow down the type of company, so if you look in investment banks, analysts can mean a lot of different things of different seniorities. So extracting skill sets, understanding whether a job requires managerial experience or doesn't, and the different ways in which we talk about skill sets. So, SQL versus relational database experience versus other types of database experience. Extracting all of that is something that we've built tools to understand, and a taxonomy of query language. And we've been doing this for 3 years now. This actually allows us to do some really cool stuff from the data science side of things. We can actually be able to compare apples to apples in jobs. And so this is an example of a job that has a similar requirements, similar skills. It might be written in slightly different ways, but also has different titles. And so we can actually start comparing the impact of different titles, of different industries, of different ways of talking about skills and qualifications by being able to compare very similar jobs. So as an example of this, I just wanted to show you what our editor does and why language and qualifications, which is the topic of this discussion, of this talk, are so important. So, this is you'd be familiar with these sorts of editors in a variety of different contexts. The Grammarlys of the world and various other augmented editors sort of give you data-driven suggestions on how to change roles or how to change the documents. And so this is sort of what we do. And I have nothing to do with the way that this beautiful piece of software looks or interfaces with this. I sort of work in the engine room of this, and so I'm coming up with a lot of the data-driven insights that go into this. And so these are the two big questions that my team asks. So we're sort of split between two different areas, and we think that's why I was so excited to speak at this conference, because on the one hand, a lot of my day-to-day is experimenting with new NLP algorithms and new data science algorithms, and this talk is actually going to come out of some experiments that we did with different algorithms. And we try and kick the tires on new technology, see how useful they are in extracting insights from these unstructured text. But on the other hand of things, and this is something I'm not going to talk about today in this talk, but I do talk about in other groups, is talking about how candidates make decisions about which jobs they apply to, how does language inform that, how do skills and qualifications inform that, and can we resolve that to sort of get broader, to attract a broader candidate pool that's qualified for those jobs. And so we very much and sort of do proprietary research on behavior as well of job seekers, because we think that data science, the natural sort of other side of the coin that really allows you to harvest a lot from data science is the decision science side of things. And so today, actually, what I'm going to talk about is the skills that we think are interested in different industries, because I'm at a data science conference. I'm going to talk about data science and tech skills, because I think that's stuff you'll find interesting. I could talk about nursing skills, but I don't think you'll find it quite as interesting. And one part of this is this idea that we want to calibrate labor supply to demand. So we want to know what employers are asking for on the one hand and try and tone that down to what skills candidates have. And that's really important to match those two, because when we have when we have mismatches, what happens is that jobs go unfilled and candidates stay unemployed for long or in terrible jobs that they don't want to work in. And so managing that is very important for the labor market. It's really important for a company's competitive ability to hire good talent and to maintain their competitive edge, because their talent is the most important thing. So this is sort of the central question that I'm going to try and answer today, is how have data science skill sets and tech skill sets changed over the last few years? And there are a couple of different ways you can answer this question. The most simple way is to do manual feature extraction. It's not simple. It's a straightforward way, but it does require a lot of work in terms of creating tools that allow you to understand, that a PhD is the same as a doctorate degree, which is the same as all of these other things. These are equivalent skill sets, and how are they mentioned in a job description? The same thing with SQL. So I just mentioned that SQL example earlier, and that Python, which might seem like a very simple thing, not all jobs that are Python jobs refer to Python. They might talk about Django, they might talk about other infrastructures and frameworks. And so extracting that information from the sort of the level that you would expect someone who's an expert Python programmer to understand is something that you would have to do in manual feature extractions. And so that's complicated. It requires you to go through this iteratively, and it also requires you to know what are the things that you want to look at, what are the skills, and so it doesn't allow you, you will create filters for the things that you expect to find. You won't necessarily create filters for things that you don't know to find, because that's part of the thing. You have to define them at the start. The other alternative are topic models, which are something that David Blei, who I'm going to refer to a little bit later, sort of popularized a couple of years ago when he was a postdoc, and this is a sort of more unsupervised method. So we don't actually go in with filters, we don't have expectations of what we think are important. What we do is we take these documents, we throw them in, and we're like, okay, these ones are tagged with 1800s, these ones are tagged with this year, and let's see the distribution and the frequency of these terms to be able to extract what we think is important in those different time points. And so I'm not a particle physicist. Apparently this example, which uses abstracts from physics papers, talks about how it sort of reflects the shift of the neighboring words to the physics words to sort of words about electrons and things like that and energy. It's showing you that there's a shift from matter to electron to quantum physics within that. That's not something that I, as a layperson, can look at those words and extract, but the point of something like dynamic topic modeling is that an expert can come and look at these buckets of words and be like, okay, I think this is this and this is that. So it does involve, even though it's an unsupervised approach from the way that you put the information into the algorithm, from the output, it does require some interaction. So obviously none of these are great, because one of the things that's the problem with both of these is we're pulling apart all these words and ignoring the context of the words. And sometimes the context actually really matters. And so I'm going to be presenting to you guys, many of you will be familiar with embeddings models for language modeling. And then I'm going to go one step further in how we manage time in embeddings models. And I'm going to talk a little bit about embeddings models and our experiments with them, because we do a lot of work with optimizing embeddings models. And I think of people who don't come into that field thinking about all the things we do, it's generally been helpful. So embeddings models, in contrast to the other approaches, don't just take words outside of their context, outside of the rest of the words that come with it. The whole point of embeddings models is that we use the context of the word to extract meaning. And so we're looking at the neighbors of the words and trying to understand what a word like, for example, Python might mean. And these are specific examples from job descriptions from looking at its context. And so if I was an alien, and this is the greatest example that you use to understand embeddings, and wanted to know what Python was, I might look at this and be like, okay, well, it clearly has something to do with programming because that seems to be a word that happens in the vicinity of Python a lot. And maybe it's got something to do with languages because that seems to happen a lot. And so you iterate through large bodies of text through that sort of process and you end up with a model that tells you that sort of information. And so it's basically, there's a lot of different approaches. I'm not going to go through each of those approaches because there's lots of algorithms in different ways. But essentially what they all do is they take these giant amounts of data, they do a bunch of dimension reduction, and then you get a 50 or a 200-fold like vector for each word. And that sort of gives you a sense of the meaning. And when you go through a second round of dimension reduction, for example, through TSNE or UMAP algorithms, you can visualize it. And so you can see in this vector space sort of projection that, you know, Python is very close to Java and C++ maybe, but it's very far away from Esperanto and some of the other languages. And so you start seeing differences in ideas that come from that. And that's been really interesting from a variety of different perspectives. And these are some specific examples that have been used on really large data sets. So you can extract hierarchies from these sorts of models. And this is really beautiful work that a Stanford NLP team did using, I think they were Google News or Wikipedia, they were Common Crawl, sorry, using documents from just generally the internet. And so what you can see here is that there's a relationship between, this is a few years ago, so some of these people are former CEOs, and the companies that they are CEOs to. And so there is an interaction, there's a dimensionality. If you think this is just a small version of the whole thing. And what I find really interesting in this is that you can extract some really even more structure from that. So you can see that all of the media companies, the Viacom, Verizon, and Vodafone are sort of clustering together, and all of the CEOs are clustering together, and there are some broad dimensions that are quite similar. We can do that with comparatives and superlatives, and so that's been a really effective mechanism of understanding language and machine translation. And the fundamental and the most exciting thing that people have done with embeddings that I think is really interesting, and I think the previous speaker was talking a little bit about, was doing the algebra on these sort of vector spaces. So we can go king minus man plus woman gets us to queen, and this is sort of the algorithm. This is some of the outputs that people have been doing. And so this was actually kind of amazing when it first came out. It's really interesting that you can sort of create meaning out of words that we don't otherwise have that structure from a lot of language text. But these are models that took billions and billions of words of text to be able to get to this point, and a lot of learning. And they have their problems. One of the biggest problems is that they reflect whatever bias that you have in your corpus. And so actually these embeddings, this is one specific example, this is a little bit of a toy example, which is very problematic, but we've also seen that embeddings that are trained on general language, on Google News corpuses, when you put them through the implicit association tests, the sort of tests that try and determine whether you're racist or sexist, end up being racist and sexist on those sorts of things, they're very, very problematic. And so there's done a lot of beautiful work. There's a lot of work that's been done to debias these algorithms, but actually there's a really recent paper that talks about how you can debias them in some senses, but you can't debias them completely. And that's because there's so much dimensionality, there's such a deep web connecting words to other words that it becomes very problematic. So how do we go through this process? And this is a process that used to take a long time to do. So you go through taking a corpus of text, and in our case we're going to be using job descriptions, doing a bunch of processing, which is probably the most important thing that I'm not going to talk about a lot today, but that's actually really critical in this process. You generate a language model, you tune it, and then you might put it in through a final application. And this has been made really easy for us because there's a lot of pre-made, pre-trained corpuses, and they have their benefits and they have their weaknesses. One of the benefits is you can see the billions of tokens, so billions of words that have gone into each of these models. The vocabulary size is huge. That's much bigger than the English language. That's because it contains all the misspellings and all of the fuzz that you typically get from dealing with online text. And there's a bunch of different algorithms, and you can also use different vector lengths. So vector lengths can impart complexity on this process, or they can also impart processing time. So it sort of depends on where your trade-off is there. Like, for example, if you wanted to put something on a phone, a native app, you might not want a 300-dimension embedding, but that would probably be fine if you were training a different type of model that really is very important. And the other sort of aspect of it is that we have different algorithms. These all have strengths and weaknesses in terms of their processing. And one of the things that's very difficult to understand from this information is how they've been pre-processed. And so that's one thing to keep in your mind as you process algorithms and as you do corpus processing. And if you want it to match what's coming out of that, you have to really understand what went into this model to begin with. There are some problems with this, and for us, we didn't use a pre-trained model. We've been training our own for a long time. There are some very, these are partly because of the subject area that we're in. So for us, IT is actually really important, but most processors, most pre-processing of these language models cause it to be either made into a lowercase, and so it would be IT would be compounded with it, which is not ideal. And then sometimes they also remove stop words, so very common words that happen that generally for most people have no meaning, but IT obviously for us has meaning. It becomes it, and then it gets removed, and then you lose that sort of information. For us, that wasn't an ideal situation. The second area is we deal with a lot of technical language. Job descriptions obviously have a lot of technical language because we're expecting people to be technical. Regardless of whether you're a chef or a computer programmer, there are a lot of domain-specific jargon that's in those, and those aren't necessarily reflected in all of the general pre-trained libraries. There are some problems also in terms of words that can have multiple meanings. So for example, drive a car, we have jobs that are for truck drivers as well as drive results, which is one of those words that happens a lot in professional jobs a lot. And we don't want them to be the same thing, because on one hand, one of them is a very active skill. On the other hand, the other one is sort of a word that you use that could be replaced by any other word. And for those of you who are programmers, chef, the job, versus chef, the language, they're both obviously very important for us to be able to resolve, but they're quite different. And so these are all sort of examples of things that we found. These were created, like if you have one of them, you can sort of surmount it by creating various exceptions, but we had all of them in such a large amount that we were like, we can't surmount this, we need to train our own with our language models. And so we did this. This is a representation, again, one of these 2D representations of a career language embedding model. And this isn't my first shot at this, but this was one of the best that we had work. And we have models, and I could give a whole talk on how you evaluate these models. People generally don't evaluate them because that's not the input. The input is what you put into your neural net or to your machine learning algorithm. So I just wanted to show you a couple of things that we saw just from the big picture analysis of this. The first is, and this didn't always happen, perks language and equal opportunity language in job descriptions, many of you would be aware, sort of tend to happen towards the end. They tend to happen very close to each other. This actually figured out that these two areas are quite distinct. They were quite far away actually in the 2D projection. They clustered very separately, but they sort of were different. So this model was able to understand that they were different things, even though they mostly co-locate together or very close to each other. And this is despite the fact that the window of these words was reasonably large. The second thing was that I think this is the really interesting thing. We talk a lot about soft skills or various types, you can call them whatever you want, but there's all different types of skills. And they actually extracted from that what are soft skills. Soft skills tend to happen throughout the process of a job description. They don't happen in one section. So it was able to figure out that these are sort of similar types of skills. And then the other sort of area that was sort of interesting was language around experience. So this was very distinct from the language around skills. It was very specific. So when you look for Python or various other types of skills, it happens somewhere else in this diagram. It's not here. So that was sort of from a big picture perspective, this worked reasonably well. So I started this talk saying that I'm going to talk to you about what's changed in data science skills and tech skills, but I'm just showing you a single projection of a single model. And so the one thing that I wanted to, actually this was a 100-dimensional model, not a 300-dimensional model, but I haven't talked about time yet. So let's talk about time. there's a lot of different methods for adding dynamic sort of embeddings or creating dynamic embeddings. On the one hand, you can do is train one of those models for every timepiece. So you just take the 2016 data and the 2017 data and train one model for each one, and then try and find out, for example, where cat is, or you use very common words to stitch them together. So maybe you wouldn't use cat in a job description thing, but you might use like soft skills, because you're assuming that they're not changing a lot, and then you're mapping all of the soft skills to each other so you can get a sense of where tracks to where, so you can then understand how they've changed over time. If it sounds complicated, it really is. It's not something I would recommend. What we found was much more efficient was to use dynamic embeddings. And these are embeddings that you get trained over time. So this was, they're trained all together. And so the goal of this is to use the statistical information that you share across these time courses. And so you don't need as much data because you're sort of assuming a certain distribution. In this case, it's a Bernoulli distribution because we're looking at words, their presence or absence. And so we use that to sort of give it a bit of structure, so we don't need as much words, and they, most importantly, don't require alignment. And there were 3 different groups at the time when we first started this project that had just released dynamic embeddings. The one that I've highlighted here in bold is Rudolph and Blei, which is Mayor Rudolph and David Blei, his graduate students' work. And that was for the very simple reason for all of the academics in the audience that they made a GitHub available of their code and some examples, and that's how you get industry adoption, okay? So the other thing that they did that was really beautiful, and this is their GitHub link, is that they had 2 outputs that were really interesting. So you didn't have to deal with someone else's morass of Tensor Flow code. You got 2 really important outputs, and this is what I think is the most important part of this. You put it through your model, and then it tells you, gives you a list of the words with the largest drift, which is fantastic. So I already have a set of words, and this is from their analysis of looking at Senate speeches over the last 120 years. So Iraq was a word that had a lot of change in Senate speeches, which is really interesting. And so it went from something that was a bit of a colonial outpost to becoming Middle Eastern, to becoming a hotbed of terrorism, to being somewhere that needs to be reconstructed. And so it's changed a lot in Senate speeches. So that was the first thing, that even if you don't need to know TensorFlow and get into the issues of graphs, you can get that information. And the second part of it was embedding neighborhoods. So it tells you what is the closest word to unemployment at each time course. So say unemployment was one of the top words, so it was something that was associated with sort of a moral sort of idea in the 1940s, and then in 2000s, unemployment became a much more of a economic term. So that's another word that's sort of gone through some shift. One thing I would say is that it will tell you what words are seeing drift, but it won't tell you which direction or what's going on. And that's actually very important for the analysis I'm going to show you. You actually need a mechanism of validating what that is. So you can understand from this that it's gone through this change. We're adding some additional ideas in terms of what that change is. You do have to intervene a little bit there in terms of being like, this is what's happened. In our case, so we were looking at skills. So really we were looking at the presence or absence or how they've changed over time. So that was a little bit easier for us, and I had a lot of skills to look at. So these are the experiments that we ran. The first experiment we ran was with a small corpus, and we just looked at all US jobs. And that's primarily because even though I'm going to talk about data science skills and I've pulled them out of this analysis, one of the things I didn't want to get into was a circular argument about how I define data science, and then go back in and we define some skills that have changed and then go back out, and you get into the circular argument about which came first, my definition of data science or the results of the analysis, and then you sort of end up in a loop. And actually this showed some really interesting results. We did this with initially, we have tens of millions of documents of job descriptions that I could have used. I decided on purpose to limit this analysis to a very small number. So this is 50,000 over the last from 2016 to 2018. So that's about 17,000 a year. It's not a lot of documents, and they're not very long either. So they're somewhere between 300 to 700 words each. We did restrict the vocabulary size because in general, these embeddings get better with a restricted vocabulary size. And we did some very basic data pre-processing. So we did do some we did pull out words that tend to happen together. So New York, for example, we didn't separate it into New and York. Like if words were much more likely to be together, there are some libraries that allow you to do that sort of analysis. It allowed them to be put together. And we did restrict the number of embedding dimensions to 100 dimensions because that was actually something that worked well. We did do some hyperparameter optimization for that, but it wasn't super important. So the two things that, one of the first things that came out of this analysis was MBA and PhD. Remember, these are all jobs, not just data science jobs. And so we looked at it. We looked at our data and actually looked at a bigger time span. So I looked at from 2016 to 2019, what's happened to MBAs. And what we see is that MBAs and PhDs in all jobs, the number of jobs requiring MBAs or PhDs has gone down significantly, which is really very interesting. MBAs don't get usually asked for in data science jobs, but I kind of wanted to look because I have seen the odd one, and it does happen, and so those have actually dropped in data science jobs. They've actually gone up in tech jobs, and that is very specifically because a lot of big tech companies, and I'm not going to name and shame them, ask for MBA for roles that you're asking for like 6 years worth of JavaScript experience as well. I don't know why. This happens, and that's just telling you that big tech is growing, not that you should go and get an MBA if you want to be a JavaScript developer for a big tech company. So on the other side of things, we looked at PhDs. What we see is the demand for PhDs is dropping in data science jobs, and we're also seeing it drop in machine learning jobs as well. And that was interesting to me because, I mean, we've seen a commoditization of machine learning technologies, things like H2O and a bunch of the other AutoML things, making this a lot easier. You don't need a math PhD on your staff to run a machine learning project. We all know that as data scientists. I'm not a math PhD either, and I run them all the time. And so the ease of open source and the commodification of some of these industries has lowered the bar significantly. We don't need as many PhDs in these roles, which sucks for people who have PhDs who are hoping that that would be a gatekeeper, but it's actually really good for the industry because it means that we're getting a broader range of voices and people with different work experience and backgrounds into it, which I think is the really important thing. I recently gave this talk actually in London, and I think this is really interesting because it shows, this is one example where we're seeing the same sort of effects. You can see the actual example of why big tech companies, so big tech companies in the US are really pushing on MBAs and tech roles, but they're not doing the same thing in the UK. In fact, if anything, it's all down across the board. And so we're seeing the same trends, even though we looked at US jobs, UK jobs showed very similar trends for some things and not others. And that was actually a really interesting source of comparison. So I just thought that was, it's an area where we don't imagine they're exactly the same, and so we see that definitely the case. One of the words that came out of this analysis was Tableau, the data visualization software. And so the pink things that I'm going to throw into some of this analysis and the gray things are the control experiments that I sort of ran, because I went back and was like, well, is all data viz up or is Tableau special? Power BI, which is it the Microsoft tool? Yes, thank you, has gone up. That didn't get picked up by analysis because I think Power BI was starting off on a very low number of jobs were requiring it. It's now sort of picked up a lot more, and so it didn't come up from the initial analysis. So I wouldn't necessarily sell Tableau and go into Power BI necessarily. Tableau is starting off a higher amount, but like data viz seemed to be up. So we went back and looked at some of our analysis and looked at data viz in general. Are more jobs asking for data viz? And what we saw was in data science jobs, we saw that was definitely there's been a growth of data viz in data science jobs, but actually the biggest growth in data viz is outside of standard data science jobs, outside of tech jobs, in fact. So that's where we're seeing the huge growth. Things, so in roles like people analytics roles, in sales and marketing, these are roles that are otherwise in most companies, they want more data viz experience. So one of the things that I tell people when I do career counseling is like, think outside of the data science box. If you have those data science skill sets, you don't need to just have them in those roles. Like there's so many, the areas where you can have the most impact are in like in finance and accounting jobs in a lot of different companies, as well as HR and various other things. So that's the first sort of hint that that's actually happening. So the other word that came out of this, which I thought was really exciting, and this sort of leads to a really interesting little story, is Hadoop. So Hadoop has actually gone down in data science jobs. This is reproducibly the case. And when I threw in Spark and AWS cloud sort of instances, what we see is AWS has gone up. It's become very popular in data science jobs as a requirement. Spark has stayed steady. And the reason, when I went back and looked at the jobs that were asking for Hadoop, what we found was a lot of those jobs were asking for you to like put up a notebook and using Hadoop. And now you can kind of do that through AWS. That's my theory, is that essentially AWS for data science roles has replaced Hadoop. It hasn't replaced Hadoop completely. Hadoop is still very important in tech roles, in non-data science tech roles. So obviously people who work in infrastructure or data engineering still need to know Hadoop. It's just stopped being the source, the technology for data scientists to share their work and to share their models. And definitely, you know, we've seen a big growth in Spark and we've seen a big growth in AWS. So that was starting, again, AWS was starting off a kind of low thing in 2016 when I did this, when I started this analysis. So I mean, it's gone through a huge amount of growth. And then the last one is this battle of the languages, which I always get a lot of questions about. Perl came out, and that's not really, shouldn't be a surprise to anyone that Perl came out of this analysis. I'd be really worried if Perl didn't come out of this analysis, to be honest. So it led to a really interesting question of like, what's happening to Python? Because I'm a Pythonista. I think a lot about, like, as in a lot of the conventional libraries that we use in natural language processing were based on string processing, things that people were doing in Perl. And so has Python replaced Perl? What we found was, okay, well, Python remained quite steady, and Java has actually kind of gone down a little bit in this time. But that's not to say you shouldn't, and so that was sort of interesting when you compare it firstly to the Stack Overflow Dev Survey, where they're seeing that Python is becoming really popular among developers to learn, versus the number of jobs asking for Python hasn't gone up. But this actually underlies a more interesting story. When we look in data science jobs, what we're seeing is that Python, again, this is in Python in data science jobs, what we're seeing is that there's been an increase in the number of jobs asking for scripting languages. So scripting languages, including Python. So there are very few, there's actually, what we've seen is that there's been a reduction in the number of jobs asking for Java, and not as many for Python. And we see sort of a similar thing for tech jobs that are non-data science roles. And so I'm actually running out of time. So I'm going to quickly just, this is the last slide, is we did the same experiment with a large corpus. And the key thing that came out of this was SQL. And we don't see any change in SQL in all jobs or data science jobs. But the big data analysis of this showed a change in SQL requirements in very specific types of roles. So we're seeing SQL being taken up in FP&A roles, in accounting roles, in biz dev, in HR roles, but not in what were the original first uptakers of SQL. And so that sort of showed us more subtle changes. So with that, I just wanted to sort of end that we've seen a change in the way of word embeddings. This is going a next level beyond to sort of give us a lot of robust results with very small data sets. And we've seen that, you know, the core things that we thought would happen in terms of data science skill sets, we're seeing more generalization, we're seeing more expansion in a lot of different types of roles. And we're seeing the commodification of distributed systems like Hadoop and of AWS is causing changes in the way that this whole architecture is happening. So if anyone has any questions, I'm so sorry for going over. Please contact me either through Twitter or through LinkedIn, or just grab me when I'm outside. Thank you so much.